Now we are going to discuss the steady state stability limit. So what is the steady state stability about? It is about small disturbances, right? So the torque angle, which is delta, that is the change in delta we consider as disturbance, and if the change in delta it is going to be very small, then it is a small disturbance, okay? And in that case, what is the limit? That is what we are going to discuss. So let us take the power angle equation. What is it? PE is equal to P max sine delta. Okay. Now we will consider a steady state wherein the value of delta we take as delta naught and the power we will take as PE naught, which is nothing but P max sine delta naught. That means if you take the sine curve, let's say some angle delta naught is here, okay, then this value, this is PE and this is delta. So this is going to be the PE naught value. At delta naught, whatever is PE, that is PE naught, okay. Now small disturbance is occurring, okay, small disturbance occurs. So let us say change in the load angle or the torque angle, let this be delta delta, and obviously there is going to be a change in the electromagnetic power as well, right? So change in PE we will take as delta PE, okay. Now at steady state, one more thing that we write here is the mechanical input. What will it be? This will be equal to PE naught, right? Because it is at steady state, there is no change. So mechanical input will be equal to PE naught. Now what will be the new electromagnetic power? New TE is equal to the old PE naught, right? The old PE is PE naught plus the change in the electromagnetic power, right? So this in terms of delta will be equal to P max sine, the new delta is what? The old delta plus the change in delta, okay. Now this sine delta naught plus delta delta we can expand, right? So this you are going to get PE naught plus delta PE will be equal to P max sine delta naught cos delta delta plus sine delta delta cos delta naught, okay. So now here our assumption will come into place. Since it is a very small change, right, this delta delta is a very small value, then what will happen to sine delta delta? This will be almost equal to delta delta, right? That is what happens when sine of a small angle, a very small value is taken, it will almost be equal to that value, okay. And what about this cos delta delta? Now this delta delta, if it is very small, then you can approximate this value to 1, okay. So here you can write down, since it is a small change, delta delta is very small, okay. So from here we make the approximation, cos delta delta is approximately equal to 1 and sine delta delta will be approximately equal to delta delta. So you will write PE naught plus delta PE will be equal to P max into sine delta naught plus delta delta P max cos delta naught, okay. Now what is this P max sine delta naught? This is same as PE naught, right? So this and this will get cancelled. So the change in the electromagnetic power, this is going to be delta delta into P max cos delta naught, okay. Now this P max cos delta naught, this is called as the synchronizing coefficient, or it is also called as the stiffness constant, and this is denoted by SP, okay. Let us now get back to the swing equation. What is the swing equation? This is given by md square delta by delta square is equal to PA, or you can write PM minus PE, right? Now instead of delta, you are going to write delta naught plus delta delta, right? So because there is a small change now, so you can replace this by delta naught plus the old delta value plus the change in delta by dt square, and this will be equal to Pn minus again Pe will be the old Pe, which is Pe naught plus the change in Pe. Okay. Now this change in Pe, you can substitute this value, right? So what you're going to get here, m, this also you can expand, right? D square delta naught by dt square plus d square delta delta by dt square. This will be equal to Pn minus Pe naught minus delta Pe is delta delta P max cos delta naught, or you can write as Sp. This term you can write as Sp. Okay. Now here this Pm was equal to Pe naught because it was the initial operating steady state, right? So this and this is going to get cancelled, and this delta naught also, it was a steady state operating angle, right? So it is a constant value. So if you are differentiating, this will also become 0. Then what will be the equation here? M d square delta delta by dt square will be equal to minus Sp into delta delta. Now this is just a differential equation. It is a linear differential equation, right? Linear differential equation, right? So we were able to obtain a linear differential equation from an initially non-linear swing equation. Swing equation is non-linear, right? So but we have succeeded in getting a linear differential equation. Okay, so because it was possible because it is a small change. Now this differential equation you can easily solve if you take delta delta as the variable, m d square the variable is equal to minus Sp into that variable. So if you solve this, you're going to get, you can get m d square plus Sp into delta delta is equal to 0. So what will be the auxiliary equation? It is going to be m d square plus Sp. This is equal to 0. Okay, so d is going to be plus or minus root over minus Sp by m. Now here m anyways it is a positive value, it is a machine constant. Sp if it is a negative value. Minus into minus will give you a positive value, root over a positive value will be a real value. Okay, so if Sp is negative, then you will get real roots, and in that case the torque angle will be increasing without any bounds. Okay, so you can verify that. Now if Sp is greater than 0, what is going to happen? This will be a purely imaginary root, right? There is no real part. If Sp is positive, this part will become imaginary and there is no other real part. So the roots of auxiliary equation will become purely imaginary. In that case, what will you get? You will get some sine or cosine function, right? So the system in that case is going to exhibit undamped oscillations or sustained oscillations. Okay, so you can write if Sp is less than 0 implies the roots are real, implies the torque angle will increase without bounds. Now if Sp is greater than 0, then roots will be purely imaginary, and in this case the system will exhibit sustained oscillations, and the oscillations will be about the angle delta naught. Okay, and the frequency of those oscillations will be omega n is equal to root over Sp by m. So now this case, the torque angle increasing without bound, this is undesirable to us, right? That is what is meant by instability. It will not reach any more steady state operating condition. So this, in this case, when if Sp is less than 0, then the system is becoming unstable, and if Sp is greater than 0, then sustained oscillations will occur, but these sustained oscillations, they can be damped out using some other damping system. Okay, so in practicality oscillations will be damped off by a damping system in place. Okay, so usually this is the damper windings in the machine. So you can write, if SP is greater than 0, then system is steady state stable about the delta naught. Okay, and if SP is less than 0, then system will be unstable. Okay, so from here you will get what will be the limit of instability, right? When if SP is 0, then the system will be at the verge of instability, right? So if SP is equal to 0, system is on the verge of instability, and this is how we are going to find out the steady state stability limit. Okay, what is SP? This is P max cos delta naught, right? So this is equal to 0. Actually here one thing that you can note here is SP, the synchronizing coefficient, I told this is equal to P max cos delta naught. Okay, so it is actually equal to the differentiation of the power with respect to d delta at the operating condition, the steady state operating condition. Okay, so this is the exact definition. So now P max cos delta naught is equal to 0. This implies that delta naught should be 90 degrees. Okay, so this is the steady state stability limit. What is the delivered power at this limit? Here PE will be equal to simply P max. Okay, now if the operating angle is going beyond the steady state stability limit, even if it is in terms of gradual changes, small changes, the system is going to fall out of synchronism. So beyond the steady state limit, system will fall out of synchronism. Okay, so we saw the steady state stability limit. This was P max, right? Now what is P max? This is equal to the sending end side voltage, receiving end side voltage divided by X, right? So we can increase the steady state stability limit by increasing these voltages or by decreasing the reactance. Okay, and as a part of decreasing the reactance, parallel transmission lines are used, and even sometimes series capacitance are introduced in the line. So this can be increased by, first method is E1 or mod E2 can be increased, or the second method is by reducing the reactance, and this is done by, here you have various methods. One is use of parallel transmission lines. Okay, and the second one is introducing series capacitance. So we have discussed about series capacitance in voltage regulation as well, right? Series capacitance will improve the voltage regulation as well, and it also improves the stability limit. Okay, so it has two purposes.